the beautiful studios of Way Happy. This is Mr. Meyer, and we are talking 18E shape of a graph. So now everything we've been doing has kind of been leading us to how we are going to do graphing, right? And the last thing that we really need, we talked about, how to find the slope, and we talked about how to find if it's increasing or decreasing, and we've had those critical points. And now we talk about concave up like a cup or concave down like a frown, right? And that's called the concavity of the graph. If you look at a graph, right, if I just randomly draw some kind of scribble like this, then you could say that this part of the graph right here is concave up like a cup, right? And what does that mean actually? That just means that all the tangent lines are underneath. All the tangent lines are underneath the graph, right? That's what that means. And then concave down like a frown means the graph looks like a frown, but more importantly, all the tangent lines would be drawn above the graph, right? So that's where all the tangent lines would be. So you have concave up like a cup and you have concave down like a frown. And what tells you that? Well, that would be the second derivative. So the second derivative, if it is negative, will tell you that the graph is concave down. And if it's positive, it will tell you that the graph is concave up. So that's just more info and another reason to do another sign chart. All right, so let's try 15a here. 15a says find the intervals where it's concave up or concave down. So that means I need the second derivative. So dy dx, the first one is going to be 6x squared minus 6x plus 4. And then remember, sign chart there would tell me increasing and decreasing. Now I'm going to go second derivative, and I am going to find out 12x minus 6. That will tell me concavity. So what does that mean? That means if I draw my sign chart, oh, by the way, I should probably solve this, right? So 12x minus 6 equals 0. So 12x equals 6. So x equals a half. So at a half, I know that there's a critical point in the second derivative, right? So there was critical points in the first derivative. Now a critical point in the second derivative. A lot of people like to write this as y double prime to remind them what it is. Put a half on here, put a critical point, and test to the left and to the right. Something smaller than a half, simple like 0. And so if I, by the way, I do like these in factored form, remember? So I would have the derivative is equal to, I'm going to change this real quick. The derivative y double prime, I guess I could have just put it underneath, is equal to 6 times 2x minus 1. And that's how I could have gotten a half. Reason being is now I can plug in a number like 0 and get 6 times negative 1, which is negative. So that part of the graph is concave down like a frown. And then bigger than a half, pick something like 5, and you would get a positive out of this. And that part of the graph is concave up like a cup. So that tells me this entire graph right here is either concave down like a frown or concave up like a cup at different points of the graph. And the concavity changes right there at a half. And that's going to be important because that's going to be the point of inflection coming up in the next section. So what about B? B is something that I'm going to have to probably factor. So f of x, I guess I should label this one B and this one A. F of x is equal to, I'm going to factor that, that is going to be x minus 4 times x minus 1 all over x minus 3. And so you can see right there that we do have oh, I was solving for zeros. Now I would like to see if anything canceled. It didn't. So now I will find the first derivative for increasing, decreasing. Yucks. This is going to be the first derivative is low d high. Low times the derivative of high, 2x minus 5 minus high, x squared minus 5x plus 4 times the derivative of low is 1 all over low, which is x minus 3 squared. I could clean this up a little bit with foiling, so that'll be 2x squareds minus 6x minus 5x is minus 11x plus 15, then minus an x squared plus a 5x and a minus 4 all over x minus 3 squared. And that will get me 2x squared minus x squared is x squared. 11, negative 11 and 5 is negative 6x. And 15 minus 4 is 11. So plus 11 all over x minus 3 squared. Now, the bad news there is that that did not reduce anymore, and I was kind of hoping the top would factor. It doesn't. So let's go on and find the second derivative, because that's really what we're after here. The second derivative is going to be low x minus 3 squared times d high 2x minus 6 minus high x squared minus 6x plus 11 times d low. Oh my goodness, that is 2 power rule. X minus 3, power it down by 1, times the derivative of the inside, which is 1, so chain rule. And we are done there. And then x minus 3 squared squared, so now to the fourth. Whew. Now, Emily's favorite, we got to look for factoring, right? This has x minus 3 and this has x minus 3. So I can pull that out. I can even pull out a 2 if I want. So I will pull out a 2 and an x minus 3. Remember the power of the smaller one. And then what do we have left? Remember, I pulled a 2 out of here. So this was an x minus, oh, that was an x minus 3 also. Dang. So I probably should have done that. But here we go. X minus 3 is left there. And here we have left minus x squared minus 6x plus 6x minus 11. We have that left over all over x minus 3 to the fourth, but I can cancel that with one of these, and now it's to the third. So does that pretty up in any fashion? I have 2 times negative x squared. Then I have 6x and 1x plus 7x. And then negative 3 and negative 7 is minus 14. I'm going to definitely pull out a negative out of there because that does not look like any fun to be had. X minus 3 cubed. And then that gives me what? Negative 2 x squared minus 7x plus 14 all over x minus 3 cubed. And I am looking, I don't think that even factors. So now I just want to solve when is this numerator equal to 0. So there's my double derivative, right? Now, when is that equal to 0? That will be my solution for my second derivative test. So I'm going to sneak that up here and say this is my f double prime of x because we want to know concavity. Now we do know that since this is a fraction, negative 3 is not existing. So we're going to have to check either side of that. And when is the numerator equal to 0? So when does x squared minus 7x plus 14 equal 0? Well, let's see. I'm going to check the discriminant first, which is b squared minus 4ac, to see if this is even real. B squared is 49 minus 4. A is 1. C is 14. So what is that? 49 minus 40 and 16 minus 56. This is a negative number. So these answers will not be real because remember, this is the under the square root part. And so that means they're imaginary. So the only critical point we have is at negative 3. And now we can go in and we can test it on the left and the right side. So plugging in something that is smaller than negative 3, like 0 would probably be the easiest. You would get a negative over a negative, which is positive. Plugging something in bigger than negative 3. Oh, I plugged in 0. That would be this side. Oh, I lied. That's a negative on top and a negative on the bottom is positive. Something smaller than, change that. That's a positive 3, right? Because yes. Something bigger than 3, like 100, I would get something negative on top and something positive on the bottom. So that is negative. And therefore, I can tell you Then on the left side, where it's positive, this is concave up like a cup, and this is concave down like a frown. All right, that moves us on to point F. Point F says points of inflection. There are two types of points of inflection, one that has a horizontal tangent line and one that doesn't. Right? If the tangent line is horizontal, or the slope is zero, or the derivative is zero, then that is called a stationary point of inflection. And if it's diagonal, then it's a non-stationary point of inflection. Stationary points are when the derivative is zero, and point of inflection is when the second derivative is zero. So that's why the second derivative is important. And this will now, example 16, kind of wrap up everything that we've had in this chapter by doing every part. So they give me a function and they want me to find all the critical points or stationary points. They want me to find all the points of inflection, increasing, decreasing, concavity, and then try to draw a sketch. So here we go. A is, I'm going to first find the derivative of that function, which is not too bad. 12x cubed minus, what is that? 3 times 16, 30 and 18, 48x squared plus 48x. So there is the first derivative. And if you want to solve the first derivative, then what you're going to do is you're going to set this equal to 0 and solve this mess. And you will see that you get factor out of 12x, and I will be left with x squared minus 4x plus 4, which is 12x. I think that factors down to x minus 2 squared. So that first derivative tells me that there is some stuff going on, right? So what am I going to do? I'm going to draw a number line. I'm going to put 0 on there because x equals 0 and x equals 2 are our critical points. So 0 and 2 are our critical points. And now if I plug in something to the left of 0 like a negative, this is always going to be positive because it's squared. So the first part is the only part I care about. So if I plug in a negative, I get a negative. If I plug in something between 0 and 1, or 0 and 2 like 1, I get a positive. And I pick something to the right, I get a positive. Now remember, this is the first derivative. So according to the first derivative, we have right here, the graph is decreasing and then increasing. So that tells me we have a minimum at 0. It also tells me that the graph was increasing and then continued to increase. So we have a stationary point of inflection at 2. So I would now they wanted me to classify the points in part A. So I would plug in 0 and say 0, 9 is a minimum, and 2 comma, I think that was 7 when I did it, is a point of inflection, a stationary point of inflection. And now that is classifying part 1. Part 2 is classify all the points of inflection. So I'm going to need the second derivative now to find out what is going on there. So part B, the second derivative is going to be 36x squared minus 96x plus 48. Yuck. I'm going to factor out something out of there. Looks like a 12 again. So 12, I'll have 3x squared minus 8x plus 4. And now this is, when I set it equal to 0, the 12 is not going to have any effect. However, when I factor the other two, that will factor out to x minus 2 and 3x minus 2. So on the second derivative, x equals 2 is a critical point. X equals 2/3 is a critical point. So I'm going to kind of take my same number line, right? And I'm going to mark on this number line 2 again at the same spot. And then there was 0. 2/3 would be about right here. So I'm going to put it there. And now there is my 2 critical points for the second derivative. I'll even label this second derivative so people know. And then again, I will test regions of this. So something smaller like 0 is going to give me a negative times a negative, which is positive. Something in between like 1 would give me a negative times a positive, which is negative. And then something bigger than 2 like 100 would give me a positive times a positive, and therefore is my and there's my sign chart. So we have concave up, then concave down, and then concave up again, right? So we have the concavity changing from one to the other at both of those critical points. So what does that tell me? Well, I still remember that 2, 7, the first derivative was 0. So 2, 7 had a horizontal tangent, meaning that it was a stationary point of inflection. But now I know at 2/3, we have a non-stationary point of inflection, and I would have to plug that in. And I remember that was kind of a gross number. So plug it into the original equation, and this is a non-stationary point of inflection. And now I can finally answer all the parts too, because I've already done in part C, increasing and decreasing. We talked about it already, right? Increasing was 0 to 2 and 2 to infinity. Decreasing is all on the first derivative, negative infinity to 0. And then part D, find the intervals where it's concave up or concave down. We have negative infinity to 2/3. We know that that is concave up, like a cup. I also had another section, my bad, 2 to infinity. 2 to infinity is concave up, and 2/3 to 2 is concave down. Now, again, you can use the included values because, again, you're talking about an interval. So notice I use parentheses. You can definitely use brackets. Um, and that is everything for that problem. Last but not least, 17, right? Let's talk about this bad boy. Find the x-intercept of this graph. So x-intercept is when y equals 0. So that means 0 equals 2 minus e to the negative x, which means e to the negative x is equal to 2. And using some fancy logarithms, I can log both sides. Ln of e to the negative x equals ln of 2. Negative x is equal to ln of 2 over ln of e, which is really just change of base formula if you wanted. So you could pick any base right there. Or ln of e is actually 1, so it's just ln of 2. So move that over. X is equal to the negative ln of 2. So there is your x-intercept. Use a calculator to approximate. Find the y-intercept, right? The y-intercept is when x is 0. Anything to the 0 power is 1. So y equals 2 minus e to the 0. So that's 2 minus 1 is 1. So the y-intercept is, this was our x-intercept. I can even write it as a point if you want. Negative ln of 2 comma 0. The y-intercept is 0 comma 1. So there's the y-intercept. Next, they want us to find when the function is increasing. So again, I will have to take the derivative. So part C, y prime is going to equal, derivative of 2 is nothing, derivative of e to the x is negative e to the x, chain rule, negative. So it's just e to the negative x. That is our derivative. When does that equal 0 is never. And so therefore, it's always positive. So this graph is always increasing. So we call that monotonic. So this graph is therefore always increasing. And then part D says take the second derivative, right? Oh, and that's what we were supposed to show. I didn't even realize that. Second derivative is e to the negative x, which is e to the negative x. But then chain rule, don't forget the negative, which this is always negative. So therefore, it's always going to be concave down because the second derivative is negative. Always concave down, and explain why y equals 2 equals the horizontal asymptote. So part D, what could I do there? I could just say that the farther, if you looked at the end behavior of this graph, if I looked at the left end, kind of like the limit as x goes to negative infinity of the function, I guess I should call it y, the left hand limit is 0. However, the limit as, or no, it's not 0, is 2, because it would be 0, but then it's 2. And then that way I could say that the horizontal asymptote would have to be 2. So I could say, therefore, horizontal asymptote is y equals 2. And last but not least, sketch the graph. And I think I forgot that on the last problem, didn't I? It's got a horizontal asymptote at 2. It's always decreasing or increasing. I mean, it's always concave down like a frown. We know where the x-intercept is. We know where the y-intercept is. So y-intercept, we know the x-intercept somewhere over here, negative. And I know it's always concave down, so it's always bending down. And so therefore, there is my sketch. That is it. Stay happy, and I'll see you next time.